Hello everyone, welcome to our DSS series. In our previous lessons, we have discussed on the time complexity, which measures how fast an algorithm runs. But there is another equally important factor called the space complexity. So let's see what is space complexity. As the definitions is that the space complexity is the total memory used by an algorithm. So space complexity is going to measure how much memory an algorithm consumes, right? So when you write a program, every program is going to use some memory, maybe in some form. Say, for example, even this simplest codes that needs space to store the variables, arrays, function calls, and the recursion stakes. So, say, think of your computer's RAM. So, RAM will come in 8 GB, 4 GB RAM, right? Think of your computer's RAM as a limited workspace. When you want to run a program, it is going to be placed into the RAM and then the processor is going to execute that program. So the more memory an algorithm consumes, the more resources it takes. This will result in slowdown of the execution or might even crash the system if memory runs out. So the main questions we have to ask is how much extra memory does my code use? Means you have to understand the space complexity. This will help us writing the efficient programs that don't waste the memory. So let's see, why does the space complexity matter? So why do we even care about the space complexity? First point is memory is a limited resource. Just now I have told about the RAM. Every program runs on a device with a limited RAM. So RAM comes in 4 GB, 8 GB, 32 GB, 64 GB. You can add more RAMs. But you know, every programs when you run, it is going to be executed on the RAM. You have to place on the RAM and the processor will execute that program. So if a program exceeds available memory, what will happen? It will might crash or slow down the system. So this is why it is essential to write a memory efficient code. Okay, all right, let's see the second point. Optimizing the space improves performance. So what is meant by the optimizing space improve performance? Say let's consider two programs. So if two programs solve the same problem, but one uses the half the memory of the other, which one is do you think is better? You will say you have to pick that the one that uses less memory, right? So we have to optimize the space. Okay, so we have to try to optimize the space uses. Just now I told you, if two programs run the going to solve the same problem, if one uses the half memory of the other, then we will have to pick the one that is going to use the half less memory. Okay, now let's see the third point, choosing the right data structure. So some data structures take up memory than others. For example, let's say arrays. Arrays is going to use contiguous memory, right? And are space efficient. They are space efficient. Think about the linked list. Linked list requires extra memory for the pointers. They are going to use the extra memory for the for what? For the pointer. For the pointer, the linked list is going to use the pointer, so they will need the extra memory. Think of the hash tables. Hash tables are fast, but they use extra space for hashing the function. So these are some data structures that takes up more memory than the others, right? So let's see the last point, the trade-off. So trade-off says sometimes to make an algorithm faster, we use extra space, right? Say for example, sorting an array in the bubble sort is slow, but it saves space. Think of the merge sort. Merge sort is faster but requires extra memory for the temporary arrays. So what you see here is that if you want to try to save memory, then the algorithm will be slow. But when you try to uh, get faster, when you want the algorithm to be faster, they will require more extra memory. So this is kind of a time space trade-off. So we have to, so space complexity is sometimes is crucial for optimizing the code. You have to pick which algorithm is best, okay, for your program. Let's see some types of the space used in a program. Let's break down how a program uses the memory. So there are three main types of space uses. The first one is the fixed space. So fixed space means, like say, this includes the constants, variables, okay, global variables, function calls. Okay, so let's see, let's take one example. Say when you want to when you declare an integer of a, b, c. So when you declare, these integers will allocate a fixed space. Okay, so only three integer size memory slots are going to be allocated in these integers. So regardless of the input size, this memory will remain constant. Okay, however, the how much input size you put, the memory constant remains constant. So let's see the second one, dynamic space. So dynamic space means dynamic, okay, means they are going to change. So this includes the data structures like the arrays, linked lists, hash tables. Okay, they are going to grow as the input size increases. Consider the say for example integer, when you declare an array of size n. So the memory is going to be memory depends on the value of n. Say if n is 1, then array will get an allocation of memory integers of 1. Okay, so if n is equal to 1000, the arrays needs 1000 integer space. 1000 integer space is going to be needed in the memory. Okay, these are called the dynamic space. Let's see the third one, recursive space. So recursive space means when a function call itself, each call creates a new stack frame in the memory. So consider the Fibonacci series, you know, right? Fibonacci fifth integer n. Okay, so if I will take this one, so if n is equal to less than or equal to 1, then return n, you know, the Fibonacci, and the return fifth n minus 1 plus fifth of n minus 2. So this is the recursive call, means calling the function itself. So this function keeps staking the function calls, which can lead to stack overflow if n is too large. So they will put on the stacks like this. If the Fibonacci is calling here, they will stack off on the memory. So if the n is too large, it will lead to stack overflow. Okay, so let's see the space complexity of some common algorithms. First one is constant space. So constant space means it is going to use a fixed memory. Means what is means independent of input size. How much the size of the input, the memory is going to be fixed. Say for example, when you want to swap the two numbers, swap of a and the b, right? When you want to swapping two variables, then take a one temporary temp and do the swapping. Okay, a is equal to b, b is equal to temp. So here this requires only one extra variable, that is O of 1 space. Okay, so the space complexity of is going to be O of 1. Consider the second one, linear space. Linear means, you know, proportional, means it's going to be proportional. Memory requirements is going to be proportional to the input size. So memory grows proportionally with the input size. Consider the array, I just now I told you. Consider the array size in the array of n. You know, this is going to, the array is going to use n memory slots. So if n is 1000, then it is going to use 1000 memory slots. So the complexity will be O of n, right? So memory is going to be growing proportionally with the input size. Let's see the third one, logarithmic space. I told you before that in the logarithmic space, say it is going to use the divide and conquer. Consider the use in the divide and conquer recursive algorithm. Say for example binary search. I told you, I give you one the example of binary search. Binary search, you know, so it's going to be divide the input size. Okay, so the area size is going to be divided into half, then again dividing the remaining half like this. So they are going to divide and conquer as you see in the binary search. So the complexity will be of log n. Okay, so only a logarithmic number of recursive calls are stored in the memory. Let's see the last one, quadratic space. Quadratic space means, say for example, when you want to store all pairs of numbers in a 2D array. Say for example in the matrix. So in the matrix, if you want to store all the pairs of numbers, so n. Okay, so it is going to use the n square slots. N square memory slots will going to be used. So if n is 1000, then it is going to use how many? N square means 10 to the power, how many numbers? 6. 10 to the power 6. Okay, so 10 to the power 6 memory slots is going to be used. So this shows how different algorithms affects the memory usage. Okay, so let's see some best practices for optimizing the space complexity. But to write a efficient code, we have to follow some best practices. So first one is use in place algorithms. So this means that we have to avoid unnecessary data structures. Say for example in the bubble sort, instead of using the extra arrays, we have swap elements within the same array. Okay, so when we want to in the bubble sort, you know, instead of using the extra space, just swap the elements within the same array. Now second point, prefer iteration over recursion when possible. So if recursion is not necessary, use loops to save memory. Okay, so the third point, choosing the right data structure. So for example the hash tables can be better than nested lists for certain lookups. Okay, the third last one, be mindful of the memory leaks. So always free of the memory. Okay, so for example in the C++ or Java, when you allocate a dynamic memory in the heap, once you allocate a memory in the heap area, then until and unless you free up that dynamic allocations, it is going to be there. Okay, the program the variable or any function is going to be used that memory heap until the program ends. So you have to manually free up the memory. Okay, so you have to be mindful of the memory leaks. Okay, so let's see the today's lessons. Let's summarize today's lessons, what we have learned today. Space complexity, you know, is about measuring the memory usage in an algorithm. Okay, so and the recursive algorithms, you know, is going to use some extra stack space. And the third point, we all optimize the memory, we have to avoid some unnecessary data structures and use the iterations over the recursions when possible. So in our next video lessons, we will dive into the asymptotic analysis, where we learn how to analyze an algorithm performance using the big O, theta and omega notations. So see you in the next video.